recording. And all right, so that should be recording. Are you able to share? Okay.
Okay, you should be able to see my screen.
Looks fine.
Okay, I think we're ready to go. So I have 4 lectures, 2 today and 2 tomorrow, about basics of QCD perturbation theory. We have something titled like that at every CTEC school. And it's a pleasure to do it. I'm sorry I can't be, or we can't all be in some common place, but I think this will work out pretty well. So first question is, why study QCD? So I want to motivate you. So suppose you're not interested in QCD at all. Do you want to discover something new at the LHC? So dark matter particles or whatever. Or maybe anomalous couplings of the Higgs bosons. Then you need to know about QCD. And I drew down here a picture of Higgs boson production going to muon and antimuon. So that's electroweak, but over here, to make the Higgs boson through a top quark loop, you've got QCD going on. So those are all gluons, and one of the gluons radiates. So you really need to know about QCD just in order to do anything. So what do people do with QCD to make applications to experiment? First of all, there's a particular calculation of Feynman diagrams. Those can get to be very elaborate and they're very difficult. But also there's some general features of the theory that enable the calculation to apply to experiment. And it's the general features that I want to talk about. I'm not going to try to tell anybody how to do calculations. So some general features, what are they? Events have a jet structure. I'll talk quite a lot about that. And then the theory uses the renormalization group, which makes the coupling different depending on the scale at which you, the scale of the process. So we call that the running coupling. And some things you can look at, which we would call observables, are computable and some are not. The ones that are computable are called infrared safe. So I need to talk a little about that. And then I want to talk about the ability to isolate soft initial state physics into part-time distribution functions. So those are some of the topics we'll deal with. And along the way, we want to study some basic processes. Electron-positron annihilation, which I'll start today in this lecture. Deeply inelastic scattering. And then hard processes in hadron-hadron collisions. So there's 3 rather separate kinds of collisions you can talk about, and they're all important. And I want to talk about some kinematics that apply to those processes. The kinematics, supposedly everybody knows them, but the way you know them is you go to a school like this one. So let's begin with electron-positron annihilation and jet production. And that's basically about the final state of QCD reactions. So I want to talk about the structure of the cross-section, general nature of the singularities in the Feynman diagrams, and then something about null plane coordinates, which is just a tool, but it really helps you to understand things. I want to talk about the space-time picture of events, which I find is enormously helpful to guide your thinking, and then about infrared safe observables. So let's get started. I want to talk about the cross-section for electron-positron goes to 3 partons. And I've written the cross-section up here. Can people see my cursor? Is it there?
Yes.
Yes.
Okay, great. The cross-section is measured in terms of E3 and cosine 1,3. Well, this is for 3 partons. So over here I have a virtual photon made by electron-positron, 3 partons coming out, a quark, an anti-quark, and a gluon. And then E3 is the energy of the gluon, and cosine theta 1,3 is the angle, cosine of the angle between the quark and the gluon. So the cross-section has the form it's written up here, some numerator that's a little bit complicated. So I haven't written it, but it's not singular. And there's a denominator E3 and a denominator 1 minus cosine theta 1,3. So that cross-section is singular when theta 1,3 goes to 0. And if you integrate d cosine theta 1,3 times the cross-section, which is 1 over 1 minus cosine theta 1,3, you'll get a logarithmic divergence. So I just wrote log of infinity. And there's a 1 over E3. And if you integrate over E3 from 0 to anywhere, you also get a logarithmic divergence. And that's a kind of a general thing. That kind of logarithmic singularities that give logarithms if you integrate them. And you can ask, where did that come from? So the matrix element, calculated from the Feynman diagram I'm showing you here, I call the matrix element just calligraphic M. That always has a factor just from the Feynman rules, 1 over P1 plus P3 covariance squared. And that is twice E1 times E3 times 1 minus cosine of angle. So right away, you see just from that propagator, there's a singularity when theta 1,3 goes to 0. And there's a singularity when E3 goes to 0. And it's just from the Feynman diagram. And anytime you have a Feynman diagram like that, you're going to have that singularity. Now there's a little secret. The numerator has the factor of theta 1,3, but not theta 1,3 squared. That comes from traces of Dirac matrices. So the matrix element squared has got 1 over E3 squared and 1 over theta 1,3 squared. For theta 1,3 goes to 0 and E3 goes to 0. And then what happens if you integrate that? So I integrate the covariant integration over P3 is D3P3 over E3 and 1 over E3 squared and theta 1,3 squared. And D3P3, if I write that out, I have a cosine, d cosine theta 1,3 and E3 squared. So in total, I've got dE3 over E3 and d theta 1,3 squared over theta 1,3 squared. That's the 2 logarithmic divergences that I was telling you about. And you see it's just completely general. It'll happen in lots of places. And just to convince you that it's general, here's a much more complicated diagram. Well, who knows what is inside of that blue blob. But in the region of momentum space in which P13 theta 1,3 goes to 0, so P3 goes to some number times P1 plus P3. then you're going to see the singularity from the propagator when 1 and 3 combine. There's other graphs in which 1 and 3 do not combine. 3 combines with something else, but there's certainly one diagram in which 1 and 3 just come together and they make a propagator with momentum P1 plus P3. So your matrix element with m plus 1 partons, where m is some number and then the 3 is the extra one, is the matrix element with m partons, so without the P3, with parton 1, 3 on shell. So this, I approximate that propagator by what it is when P1 plus P3 squared is 0 in the limit in which it goes to 0, and some kind of spinors in 1 over P1 plus P3 squared. So that's the same structure that we looked at in the previous slides. And the spinors divided by P1 plus P3 squared is your splitting amplitude. And to get a contribution to a cross section, you just square that. So that is how one starts to define the parton shower, which a large part of this school is about parton shower programs. So you just put that kind of thing into your parton shower. Oops, went too far here. So that picture suggests the structure of events that you're likely to see in electron-positron annihilations. You have partons and they split into, starting at the hard interaction, 1 parton splits into 2, and then each of those split into 2 more. Those are all those splitting amplitudes squared. And it just keeps going. That's going to lead to partons with small angles between them and partons with even smaller angles between them to make a structure in which things are becoming more and more collinear. So that's the theta 1, 3 goes to 0 limit. Or you can have something, if it's a gluon, that's really soft, that is, its energy is going to 0. So sometimes a soft gluon is emitted not collinear to its parent parton, but it's just soft, indicated that with a kind of a wide angle here, or here's another one. So what does that tell you about the structure of the final states? It's a picture like I drew down here, where there's a spray of particles going out one way, a spray of particles going out another way, with rather small angles, and then some particles going out sideways, but with very small energy. So I drew 2 sideways going ones. Those are soft particles. And those sprays of particles we call jets. And those are seen in nature. And just to show you that, I copied a picture from Atlas. This is an evented atlas in hadron-hadron collisions in which there's 2 jets. So I have to tell you what I'm plotting here. The axis labeled eta is a pseudo rapidity. It's basically the angle from 0 is the center of the detector, and then -5 is way small angles going in one direction. So angles away from the beam. And phi is the azimuthal angle going around the Atlas detector from 0 to 2 pi. So here, right in the middle at phi equals pi and eta equals roughly 0, there's lots of transverse momentum. So the vertical axis is transverse momentum, how much transverse momentum there is in each little bin of eta phi. And there's a lot. So this is 120 GeV per bin in one bin. So that's got 120 GeV and this has got 80 GeV. That bin has 40 GeV. Lots of transverse momentum, and it's all in a very small angular region. So that's a picture of an experimental jet. And here's another jet. So there's two jets seen in this event with rather a lot of transverse momentum. This is an unusual event, but of events in which there's lots of transverse momentum seen, it's always like this. It's not that there's transverse momentum seen all over the detector. The transverse momentum groups itself into jets. Some, usually two, sometimes three, sometimes four jets. And if you just look at an event display like this, which is usually called a Lego plot for obvious reasons, that's what you see. Oops. So let me talk now about just a technical matter, no plane coordinates. It's a very convenient way to do kinematics. So if I have a particle with momentum p, I can take the components of p to be p plus, p minus, p1, p2, where in the coordinate system that I'm using, p plus is p0 plus p3 over square root of 2. And p minus is p0 minus p3 over square root of 2. And 1 and 2 are the transverse directions. So at p3 equals 0, the mass shell for that particle, p squared equals m squared, is this orange line. And it gets to be tangent to the p plus axis in one direction and tangent to the p minus axis in another direction. So what you can do to analyze events or analyze the theory is choose your axes so that relative to the axis you're chosen, the particle momenta for some group of particles, like particles in a jet, have small transverse momentum. Then the picture of for all the momenta tends to look like this, and they have large p plus or alternatively large p minus. So let's look at some properties. P plus minus, or call the definition, that makes the covariance squared of p. P squared is twice p plus p minus, minus p transverse squared. And for a particle on its mass shell, p plus always has to be positive and p minus is always positive if p squared is positive, just like in this picture here. And if I solve this equation we have up here for p squared, then p minus is p perp squared plus the mass of the particle squared over 2p plus. So if I've arranged my coordinates so that p transverse is rather small, say a GeV, but the total energy is big, 100 GeV, so then p plus will be large, and if I chose the axis in the right direction, and p minus would be small. Well, if it's 1 GeV squared divided by p plus, so that's like 1 over 100. So p minus is 10 to the minus 2 GeV. And integration over the mass shell, what does that look like? Let me just make sure I got the right slide here. D3P over E, that's your usual covariant integration over the mass shell that you're probably familiar with. If you just change coordinates to plus minus and transverse coordinates and put it on the mass shell, that's D2P transverse and dp plus over 2p plus. So it's really simple. The other thing you need to know about this is how about if there's an x? So if I'm doing a Fourier transform, So exponential of e to the I p dot x integrated over p. Well, what is p dot x? It's p plus times x minus plus p minus times x plus minus p transverse dot x transverse. So x transverse is Fourier conjugate to p transverse. That's easy. But x minus is Fourier transfer conjugate to p plus, and x plus is conjugate to p minus. So in taking Fourier transforms, you just reverse the plus and minus. That's a little inconvenient, but it's easy enough to remember that. And how about the behavior of that under boosts? Supposing I have a boost along the z-axis, then, and v is any form momentum, then the new v plus is the boost angle, e to the omega times the old v plus. And the new v minus is e to the minus omega times the old v minus. And the transverse components don't change. So then p dot x, the p minus plus gets to be bigger, the x minus gets to be smaller, it's unchanged. P dot x is unchanged under this. Well, it's a Lorentz transformation, so it better be. And the boosts are really simple using the plus minus components. It's just you scale the plus components one way and you scale the minus components the other way. So that helps us to think about the space-time picture of singularities. So here's a Feynman diagram, same one we were looking at, P1 and P3, and then P1 plus P3 I called K. And just consider that amputated Feynman diagram. So I cut off the propagators for the external legs. What does that look like? And let me choose coordinates so that K plus is large and K transverse is 0 or small. So then K squared, which is in this frame 2K plus K minus, becomes small when K minus becomes small, which is either the collinear or the soft limit, taking the masses of all these partons to be 0. And in that case, if you just work out the kinematics, K minus is the sum of the minus momenta of 1 and 3. So it's P perp 3 squared over P1 plus. P perp 3 and P perp 1 are the opposite in this reference frame. And plus P perp 3 squared over to P3 plus. So the lesson is K minus is getting to be small in this collinear limit. So now consider what the Fourier transform is. The singularity corresponds to large K plus, small K minus. And now if I take a Fourier transform, integration, well, SF of X instead of SF of K, where SF is the propagator here that's in orange, is exponential of e to the I. Well, recall K plus X minus plus K minus X plus minus K perp dot X perp. So if the K minus is small, then the contributing X pluses in the Fourier transform are big. And similarly, if the K plus is big, the corresponding X minuses are small. So space-time picture of just this diagram is here. I've made electron-positron annihilate kind of right around the origin. The virtual photon is way far off shell, so it doesn't go very far before it splits into Q cube R. And then here's where the quark goes. And it goes a long way in X plus and not very far in X minus. So it's just like I drew it. It's not exactly along the X minus equals 0 axis, but just about in a long way in X plus. So singularities of QCD correspond to particles traveling a long way in space-time. And what that means is in this picture that I was using to talk about momentum space and where particles are in momentum space, we can talk about the same thing in position space. Then a particle comes along and splits after a while, and then it goes along and splits later. And suppose this is a jet, supposing it's going more or less in the plus direction, then the separation in x plus, in position, is big between the initial and the final end of the propagator. Well, big, pretty big compared to 1 TeV, inverse 1 TeV, which is a very short scale for the hard interaction. But this propagator is even smaller, K minus, so it's even bigger X plus. So this separation in time, or in X minus, X plus rather, this separation is even bigger. So the idea is that there's an initial splitting that happens pretty far from the interaction in terms of inverse TeV, but not so far. So maybe 10 to the minus 3 Fermis. And then the next one is much further apart, say 10 to the minus 2 Fermis. And the next one is even further apart. So the time scale's getting bigger and bigger. It was hard to draw in this graph, but I should have drawn these things way spread out in time. So now what? We're going to find out that QCD cannot predict long-time physics very well. It's because of the running coupling. The running coupling runs to get bigger as the time separations get to be bigger. So you can't really predict long-time physics. However, the detector is a long distance away from the interaction. The interaction, the scales you want to use are inverse femtometers, and the detector is at least millimeters away, and parts of the detector are meters away. So how on earth can you have any kind of predictions from QCD, given that the detector, where you really see things, that's a huge distance away? So we have to talk about infrared safe observables. And here's the definition. The observable I call F. So observable is just something you can measure. And the cross-section for observable F is in terms of partons, one. So this is for if there's 2 partons. The next line is if there's 3 partons. The next line is if there's 4 partons, and so forth. And it's the cross-section computed in perturbation theory for the 2 partons. In electron-positron annihilation, notice what can you have? 2 partons, all there is the angle relative to the beam. So I call those angles theta phi is omega 2. So d sigma d omega 2, and then some function that you're going to measure. That's a function of P1 and P2. Or if you have 3 partons, then it's cross-section to make the 3 partons. So I've added a new variable, dE3, d omega 3, and some function F3 that's a function of P1, P2, P3. And similarly for 4 partons, there's F4 of P1, P2, P3, P4. So that would be for any observable you might want to look at, as long as I can think of it at the parton level. And that observable has the property that it's infrared safe. That's a technical definition. If for Z goes to 0, or Z is somewhere between 0 and 1, F for m+1 partons, where the last two partons have momentum 1 minus z times some pm, or z times pm, for the two partons. So those are two partons that in this limit are collinear to pm, with a momentum fraction z 1 minus z. And z could be 0 here, so if z is 0, then the last parton is soft. And the criterion that I want to have is that the measurement function when two partons become collinear is the measurement function for one fewer partons, Fm, with just Pm instead of these two momenta. So that's in the limit. Fm+1 at the limit of collinear or soft emission is Fm with that substitution here. And if the Pm and Pm+1 are approaching that limit, I want to have a smooth limit so that the left-hand side of this equation is a good approximation to the limiting form. That means that those F's should be smooth functions. If they're not smooth functions, if they have delta functions or theta functions in it, then you should worry a little bit and check to see if that not smooth functions messes up the infrared safety. Okay, so what does that mean? It means in a physical event, the actual event gives approximately the same result as if the hadrons in a jet are combined to make a few parton jets. So imagine over here on the left, those are all partons, but this parton and that parton are almost collinear, so it's as if you combine them to make one parton. Now that little jet has only 3 partons, and combine the next closest ones. Finally, just combining everything, you get the right-hand picture where there's 3 very high momentum jets. So your physical event, provided I apply the same algorithm to hadrons as I apply to partons, the physical event has almost the same measurement as a partonic event with just 3 partons. And so that happens if you're measuring something that's infrared safe. And in calculated cross sections, the infrared infinities that you get from those singularities, they cancel. That's because there's a cancellation between a real emission diagram, like the one I drew on the left, that we've been talking about all this time, and an exchange diagram, where this is a virtual gluon and it's exchanged. And you may know that Feynman diagrams, if you integrate real emission diagrams and then add on the corresponding virtual diagram, infinities would tend to cancel. And that's what happens. So in real physical events, the event you see in the detector looks almost like a parton event, so the measurement function is just about the same. And in a calculation, that property allows cancellation of the singularities between real diagrams and virtual diagrams. And what's the simplest example of an infrared safe observable? Is the total cross-section. So that's if all the FMs are equal to 1. Then you just measure the total cross-section. And then there's infinities in various individual diagrams, but they'll all cancel. And a more interesting example is the thrust distribution for electron-positron annihilation. So there, the FMs really consist of delta functions. If we want to measure d sigma dt, where t is an object called the thrust, and the thrust is t sub m for m partons of all those momenta. And the thrust for m partons is now, it's a kind of a complicated definition, but we can just work through it. You sum over all the partons, or if it's hadrons, you sum over all the hadrons. And in the denominator, you have just the sum of the absolute values of the momenta. And that's the energy, because I suppose these are all massless particles. Or in physical, for hadrons are almost massless. So sum of the absolute values of the momenta. And then in the numerator, sum of the dot products of the momenta, 3 momenta, with a unit vector u. And that'll give a different answer depending on what the u is. But you take the biggest answer you can get by changing u. So the direction u that gives the biggest ratio there is called the thrust axis. And for this event that I've sketched out here, the thrust axis is this black dotted line. So the black dotted line, if I dot into PIs into that U, it makes those PIs the biggest that they could be. Either big positive numbers or big negative numbers, but I take the absolute values here, so it doesn't matter. So there's the thrust axis for this event. And once you've found the thrust axis, then the thrust itself is just that numerator divided by the denominator. And actually, if it's an event like this, then pi.u is almost the absolute value of pi. So the thrust is almost 1. So that's a observable in electron-positron annihilation. It's been used for a very long time. And what you may note is that if there's any particle here which has 0 momentum, it just drops out of the numerator, it drops out of the denominator. So very soft particles don't count. And if 2 partons or particles become collinear, then what happens? You have 1 minus z times some pm dot u plus z times pm dot u. And I don't need the absolute values if I just take the PMs to be more or less along u. So those are all positive. Then it's z plus 1 minus z is just 1, so it's pm dot u. And in the denominator, 1 minus the absolute PM plus Z PM is just PM. So in a collinear splitting, the collinear splitting doesn't matter. That's why this is an infrared safe observable. So since the thrust distribution is infrared safe, you can calculate it in perturbation theory. And people, of course, long ago did that calculation. And here's the result, d sigma d thrust. So it's proportional to alpha strong because there has to be at least 1 splitting. Otherwise, the thrust is just 1. And there's a polynomial in t times 1 over 1 minus t. And another polynomial divided by 1 minus t times a logarithm, which has got a log of 1 minus t. So what you'll notice is that it's singular as t goes to 1. And I put in a q here. Q is just the total momentum of the event. And CF is a color factor 4/3. So d sigma dt is singular for thrust goes to 1. That's perhaps not a surprise. And nevertheless, I claim that the thrust distribution is infrared safe. So let's just talk about that a little bit. I want to talk about a quantitative measure for infrared safety. People don't usually talk about that, but I think it's useful. So one says an observable F is infrared safe or it's not infrared safe. So it's infrared safety has values yes or no, or 1 or 0. But you can talk about how safe it is. So you can say it's safe at scale Q squared, which depends on F. So what might that mean? Imagine a splitting. So parton M goes to parton I plus parton J. And let's just define a splitting scale, mu squared, which is Q over the energy of the total, EI plus EJ, and then PI plus PJ squared. So PI plus PJ squared goes to 0 in a collinear or a soft emission. So mu squared goes to 0 in a collinear or soft emission. So my mu squared is just a measure of how collinear or soft the splitting was. And the limit that you're interested in then is mu squared goes to 0. But if mu squared was something and then it goes to 0, there's a change in F for mu squared not 0 minus mu squared equals 0. F here is your observable. So the question is, how much does F change? Well, the change in F induces a change in the cross-section. And the change in the cross-section we could call delta sigma. And now I can define the infrared safety scale corresponding to observable F. And 1 over that scale, Q squared of F, is the maximum of the rate of change of the cross-section, logarithmic rate of change, so d sigma divided by how collinear that is, in the limit as mu squared goes to 0. So and if there's many terms here, you just take the biggest one, so the most sensitive one. That makes your Q squared the smallest it could be, according to that ratio. Okay, so it's a ratio, that 1 over Q squared is telling me the sensitivity of the observed cross-section to soft or collinear splittings. And what is it for thrust distribution? So you have to just do a little calculation and you find that the change in the thrust is the thrust itself times mu squared over Q squared, where mu squared was the splitting scale. And sigma of F is approximately 1 over 1 minus thrust. So d sigma over sigma is delta t over 1 minus t. And if delta t is what's on the top, that's t over 1 minus t mu squared over Q squared. So now recall the definition of Q squared. Q squared was mu squared divided by delta sigma times sigma. So I now substitute delta sigma over sigma. So sigma over delta sigma instead, 1 minus t over t, Q squared over mu squared. The mu squareds cancel, and the infrared scale for the thrust distribution is then 1 minus t over t times Q squared. So what do I conclude? If Q squared of F, well, if t is close to 1, so a half or something, or 0.8, 1 minus t is not a really small number, so Q squared of F is just of order Q squared. However, if 1 minus t becomes small, then Q squared of F is going to 0 because it's proportional to 1 minus t. So let me just go back. The cross-section has 1 over 1 minus t and logs of 1 minus t. So something's sort of going wrong. You're getting big logarithms when t goes to 1. And this is just a reflection of that. the scale for the thrust distribution is not q squared. It's 1 minus t times q squared. So as 1 minus t goes to 0, the thrust distribution is less and less infrared safe. Okay, let's just review what we've had. QCD Feynman diagrams are singular when any two partons become collinear or when a gluon becomes soft. And singular, I mean, that's a real singularity. Something's going to infinity, but that means that the diagrams get to be big in just that limit. And if you want to keep track of big things and neglect small things, then you can use the parton shower Monte Carlo, because the parton shower Monte Carlos are designed to reflect the singularities of QCD, those 1 over P1 plus P3 squareds. That's what's built into the parton showers. And all this structure of QCD has a real physical result. It means that the final state's going to look like jets. And that's pretty amazing. Long ago, when the energy available, say in electron-positron annihilation at DAISY laboratory, was 34 GeV, there were jets, but the jets were sort of indistinct. Their angular spread was not really tiny, and it wasn't so easy to see them. But now at LHC, when there's enormous energies available, the angular separation of partons in a jet gets to be quite small, and it's just evident from looking at these event displays that final states look like jets. And let me just emphasize that if you have an event with, say, the two jets like we looked at, with total transverse momentum, absolute value transverse momentum was about a TeV, I think, for that event. If you look for all events with total transverse momentum of 1 TeV, they're always jet events. It's not that the 1 TeV is spread all over the Atlas or CMS detector. It's they look like the pictures that we looked at for a particular event. When we look at space-time, the small virtuality splittings, that is either soft or collinear, those happen late in time. It's spread out in space-time and later for a smaller and smaller virtuality. The other point we emphasized was that you can look at the small-time physics by using infrared-safe observables. And infrared-safe observables have a scale associated with them. Sometimes the scale is really just the biggest scale around, but like for the thrust distribution for T close to 1, that scale can be small. When the scale of your observable is small, but there's a bigger scale around, like the center of mass energy of electron-positron annihilation, then there's 2 scales that are quite different. And there's a possibility, even probability, that computed cross-sections will contain logarithms of the ratio of those 2 scales. So that's why we saw the thrust distribution cross-section has log of 1 minus t in it. 1 over 1 minus t times log of 1 minus t. And when that happens, people want to sum those large logarithms, to figure out the terms with the biggest logarithms per power of alpha strong and sum them all up. And there's a huge industry to do that analytically with soft collinear effective theory. And parton shower algorithms can partly do that, sometimes really well, sometimes not quite so well, but they're more or less designed to reflect the singularities of QCD, so they should do a fairly good job of summing those soft singularities. Okay, so I'm ready to move on to renormalization. Let me just take a little break here and ask if there's, I know I see a hand. Rock Medvis, did you have a question? We could do a question.
Yes, I was just curious. Is there any particular reason why we didn't mention collinear safety? Why we focused so much only on the infrared safety?
Oh, it's the words I choose to use. So I put it all together. I just call it infrared safety. Infrared safety means safety with respect to collinear emissions and with respect to soft emissions together. You're not infrared safe unless you're safe with respect to both of those.
Okay, thank
Sometimes people use the word soft and collinear safe. To my mind, you always want to talk about them together, so it's kind of silly to make a distinction like that. So we just call it infrared safety. There's another hand who's, I don't see a name for that.
Yes, hi, it's me. Hello, can you hear me?
Hi, yes, I can hear you barely.
Okay, I'll try to speak louder. So I don't have any specific questions. Only I want to request if you can explain. So on slide 11, so you mentioned how
I'm not hearing anything at all.
One second, sorry.
Yeah, you said slide 11. I heard that part. I think you wanted some explanation of that, but go ahead if you can be louder.
How about now? Hello?
Yeah, that works.
Okay, perfect. Yeah, so I was saying I don't have a specific questions, but I would appreciate if you can explain a bit on slide 11. So you say on the top diagram that you have m+1 partons, and then you mentioned how this amplitude is approximately equal to this formula here. So I would just appreciate if you can maybe elaborate a bit.
Let's see. We were looking at the formula for infrared safe things.
That's slide 11.
Or this one. So what about this? Is this formula you wanted?
No. 11.
Slide 11.
22. No? The numbers on the bottom. Yes.
Yes.
Yeah. So here, how is the bottom? I mean, how did we come about the equation on the second equation?
So the idea is I have this complicated Feynman diagram. You can imagine all kinds of stuff inside of that blue blob. There's many diagrams in which I can combine all those partons into one. So far, I'm just looking at tree diagrams, so not virtual loops. But I want to know what happens when P3 gets to be collinear with P1. So P3 is approximately Z, some number Z, times P1 plus P3. I could, by the way, have considered P3 getting to be soft, in which case Z is 0. So what happens there? Out of all the diagrams there are for the amplitude, some of them are singular. And how does a diagram get to be singular? It gets to be singular when it's a diagram that has the structure of the bottom one, where P1 joins P3 and makes the propagator with momentum P1 plus P3. That diagram is singular because it's got a denominator P1 plus P3 squared. And once I've got that, then I just look at those diagrams and I look at, so those are the diagrams with singularities. And 1 over P1 plus P3 squared goes to 0 in either the soft or the collinear limit. And then you get to the picture that we were talking about on that previous slide. You get the dE3 over E3, d theta squared over theta squared. And that's just very general, that you look at all diagrams, you ask yourself, is there a singularity? And find the diagrams for the singularity. So those are the diagrams where P1 and P3 join. So it looks like a parton splitting in the language of parton showers. And then you find this kind of singularity. And it's just a characteristic of QCD. Does that help?
Okay, yeah, that's much clear now. Thanks.
Okay. There more questions? Jay Sandeshra?
Yeah, that was me. Sorry, I'm low, man.
Oh, that was you. Any more questions? Okay, I think it's probably wise to just end this now, and then I'll go back in the next lecture to renormalization group and the running coupling. We'll just start there. And I think we have a half an hour break.
Yes, that's correct. So everyone can take half an hour, pull up a coffee, and we'll start on the half hour. And I will stop the recording, and we'll email you about the details of where you can find the recordings later on, whether they're on the CERN system or we'll upload them separately. But so we'll see folks in half an hour. So thank you.
Okay.